Hello and welcome to Module 21, Cryptography. So this is a big chapter, so we may take several videos to do this, maybe a couple, but please take notes and do me a favor when you when you're watching this, watch it in chunks because it can get complicated and I'd like you to take your time watching this. So spread it over maybe several times, maybe 20 minutes a piece or so. I don't know. I don't know how long it's going to take, but whatever it takes, do it in chunks so you retain a lot more that way. But I'll try to shed a little bit of light on the complexity of cryptography and how it works. Okay, so we will cover integrity and authenticity, what is confidentiality and how we can achieve that using cryptography, public key PKs, the PKY, the public key cryptography will explain how that works, the authorities that issue digital certificates and things like that, and we'll talk about the applications and the impact of cryptography towards the end. Okay, so 4 elements for securing communication. So we make sure, so we're talking about now just data and how to make sure that data is secured. Data integrity, please write these down. All these 4 things, that's what cryptography allows us to have. Data integrity, that means that we are going to make sure that the data that is being sent is received and has not been altered. That's called data integrity, or the data that is saved on the drive when you pick it up. It is the data that the same data that you have saved. Origin authentication, you are going to make sure that the data that is being sent you're going to authenticate the user, that it's the person who is sending it. You're going to make sure the one who's sending it is the one that actually did send it, the one that, it's not forged in any way. Data confidentiality, which is a big thing. This is going to guarantee and make sure that only authorized users are able to see the message, because we encrypt the data with a key, and the sender and the receiver has those keys, and so therefore only the sender and the receiver will be able to see the data. So that would protect confidentiality that way. And non-repudiation. Non-repudiation means I'm going to make sure that no one's, if you send me a message and I received it and I was able to decrypt it, you're not going to be able to say, no, I did not send it to you. That wasn't me. Okay, so it's almost impossible to do that. Repudiate that you have not sent the data. So that's called non-repudiation. So it's a really, really nice way of doing it. Let's start with the hashing algorithms. The hash is it does not really encrypt data. So what it really does, so do me a favor, write down all the bullet points on the hashing algorithm. So you need to understand what the hashing is, and I'll explain it to you. So listen to what I'm saying. If you have a message, no matter how big the message is, or it could be just as small as a password. So you take that message, you throw it into a hash algorithm, a program, and then the program will look at all the data that's written in the plain text message or your password. It will look at the capital letters, lowercase letters, you name it, everything, and will come up with a number, a fixed number, fixed length. So let's say whatever this number is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14 character length number. And it will always be 14 character regardless of how big this thing is. Okay, so once it goes through the algorithm, depending on what the wording are, the capital letters, symbols, whatever, I'll come up with a special number unique to this. This is called a hash or a ciphertext. Therefore, looking at this, if somebody sees this, there is no way they'll be able to give the plain message back. So it's impossible. This is like grinding coffee. Once the coffee is grinded, you will never be able to get the beans back. That's what the hash algorithm for. So you can actually, that's what we do with password. We save the hashes on the hard drive, right? So when you type your um, password, we run the same hash and we compare the hashes on the hard drive. So if somebody steals your hard drive and gets the hashes, they won't be able to know what your password is, right? Unless you typed a word that is known to everybody, like a dictionary word. So I'll steal this and I'll run the hash program on all the words in the dictionary and I'll try to match the output. And if I get a hit, I know what your password is, right? So that's why you should never use a common word for a password. All right, so that's what hashing is. Now, so that's exactly what I just told you. So we can skip that. Message digest number 5 is a typical hash program that is used. We use that a lot in the Cisco routers. That would also encrypt the data. And there is the secure hashing algorithm. This is mostly used on routers and Cisco routers to encrypt passwords. The secure hashing algorithm is used mostly for VPNs. Microsoft has their own hashing algorithm for their own uh, password that you really installed on your computer. All right, so the message digest number 5 uses a 120-bit digest. So this is the old, but it's still pretty powerful. Then you got SHA-1, the secure hashing algorithm, 1, 2, 3. So SHA-3 is the most powerful, right? Because it has very long bits of algorithm, comes up with big hashes, right? So that is definitely what you want to use if it's available. So please write down these 4 well-known hash functions and know that the hashes SHA-1, 2, and 3 are mainly used for VPNs. MD5 is also used, well, it could be used for MD VPNs, but it's typically not. It's mostly used for passwords, specifically on routers and switches. All right. Not only write down what the functions are, but write the definitions of each. All right. So let's take a look at the origin authentication. So if somebody sends me a message and they hash it, somebody may be able to take that message and decrypt it, decrypt the hash. So what we do is we can use the HMAC. That means we're going to add a key, encrypt the hash that comes out with a key. So you have to have a key to actually see the hash. So you don't have to, you cannot mess it up while it's traveling on its way. That's what the HMAC. So that is adds an additional layer of security when you add a secured key with the hash. So, and please write this down. The message authentication code MAC, the HMAC, is used by SSL, IP security, and SSH. So it's used all over. If you use an HTTPS, you're probably going to use that as well. All right. So write down the first 2 bullet points for HMAC algorithm. So what you do is you're going to get the hash, and when you get the hash, you are going to encrypt it with the key, the hash, that is. So there's the hash, there's the key, and you get the HMAC, right? And this is sent to you. So when you get this, you have to decrypt this to actually see the hash first before you put your data in the hash program. All right, so that's how HMAC works. So HMAC is also used on Cisco routers, OSPF, when routers pass updates to each other. They use HMAC hashing to encrypt the updates that they send to each other, right? Okay, let's take a look now at confidentiality. Confidentiality is when we encrypt the data. Confidentiality meaning, again, no one is going to be able to see the data except the sender and the receiver. And how can we achieve that? Is we'll have keys to encrypt the data. The sender and the receiver will know what the keys are, and we'll use these keys to decrypt the data. So please write down these 4 bullet points for symmetric and these 4 points for asymmetric encryption. There are 2 types of encryption. There is symmetric and asymmetric. And symmetric encryption means, please also write these down up here, these bullet points. I think this page is very, very important because it covers a lot of the stuff that we're going to be discussing from now on. So symmetric encryption means the sender and the receiver has the same key, and they encrypt and decrypt the data using the same key. Pre-shared key, sometimes we call it, right? The longer the key, of course, the better. The advantage of this encrypting and decrypting the data becomes very, very quick. But the problem is, of course, is the compromising of that key. If somebody gets that key, and then they'll be able to decrypt all the data that's being sent and received. And also, it becomes very, very, and how do you get that key to the sender? But we want to use asymmetric encryption. On the other hand, you have asymmetric encryption. Asymmetric encryption, sorry about that, becomes a little bit more complicated. You have 2 keys, a private and a public key. If you encrypt the data with 1 key, you have to use the other key to decrypt the data, and vice versa. So it makes it a little bit more challenging because you'll have a key that you're not sharing with anyone. That's going to be your private key, and the other public key, you'll give it out to whoever wants to send you data. We'll discuss asymmetric encryption in a few minutes. So let's talk about symmetric. Again, symmetric is having a pre-shared key. You're sharing the keys between them. You are going to take the data, encrypt it with this whatever key you have, and you'll get some encrypted data. When you receive the data, you decrypt it with the same key. That's it. And there are 2 types. There are some of them called block cipher and stream cipher, the symmetric keying. So you need to know the difference between both. So please write this down. Block ciphers, what they do is they take blocks of data and they encrypt them with the key. Right? You get blocks of data. That's called block ciphers. DES does that. And EES does that as well. It's a little bit longer than stream. So write this down too. Stream ciphers is they do it bit by bit or byte by byte. And it's much quicker because you're constantly encrypting the data. Okay, the other guy on the other hand is using the same decrypting data. You're doing that with RS4. This is for the RS4 is the WEP for wireless, WEP, the weakest encryption method for wireless networks, or your GSM phones. You're having AT&T or T-Mobile phones, or they use cipher stream symmetric encryption keys to encrypt your data. All right, take a picture of this. These are the different types of symmetric encryption algorithms that are out there. DES created many years ago from the 1980s. IBM, if I recall, is the one that came up with it. You got the triple DES. They have 3 keys to encrypt, decrypt, and encrypt the data. Still pretty much used, even though it's saying here that it's going to be retired in 2023. This is the most widely used, the AES. This is the WPA2. WPA is the encryption method that is used in wireless network. There's WP3, WPA3, which is what's recommended nowadays. But you have 256. It's almost impossible to crack the AES keys too. So then you got the software Then you got the seal, the software optimized encryption algorithm, has 160-bit encryption keys. Then you got the reverse ciphers, RC4 and so on. They have or even RC6, which is pretty competitive with AES. Very, very strong keys. So most likely you'll be using AES from now on. Asymmetric. So let's talk about that. So when you're talking about asymmetric keying, please write down all the bullet points for asymmetric keying. And let me, while you're doing that, listen to how asymmetric keying works. So the way it works is, let's say I want everybody that wants to send me data. So what I want to do is I'm going to create two keys. One key I keep, and one key I give it to everybody that wants to send me data. The one that I give out is called a public key. The one that I keep is called the private key. Now, anybody that encrypts the data with the public key and sends it to me, the only person that is going to be able to decrypt the data is me, because I have the other key. When you create the two keys, if you encrypt the data with one key, you have to decrypt it with the other. Okay? So when I send out the public key, everybody needs to use that key to encrypt the data, and they send it to me. If somebody captured that data on the way and they try to decrypt it with the public key that I gave out, it's not going to work, because the only person that is going to be able to decrypt it is me, because I have that private key. Is that clear? So that makes it very, very strong, because I'm not sharing. That's why we call it private. So that's how symmetric keying works. Beautiful, right? And I can go the other way around. So if I want to tell you that, for example, there's no class on Thursday, right? I will write the message and I will encrypt the data with my private key, right? And I'll send it out to you. And you can be able to use your public key to decipher the data, because you have the other key. You're going to say, yeah, came from Professor Awad. Why? Because you were able to decipher the data. If somebody else sent it, Mary sent it for your classmate, she used the public key to encrypt the data. And if she did that and you received it, you're not going to be able to decipher the data, because you have the same key as she does. You cannot encrypt and decrypt the data with the same key. So it must came from me. Is that clear? That's you can verify the authenticity, right? The sender. And right? So that's how we can make sure we can provide the authenticity of the sender. And on top of this, I cannot repudiate. I cannot say I didn't send that message, because it's impossible. Who else could have sent it? The only reason you were able to decrypt the data is because I used my private key to encrypt it. And I'm the only one that has it, right? So that's how we gain confidentiality, non-repudiation, authentication of the sender, and so on. All right? Take a picture of this. This is the three different types of, although there's another one called the RSA, asymmetric keying. The Diffie-Hellman is most, by the way, so why aren't we using asymmetric keying instead of symmetric keying? Well, because asymmetric keying is very, very slow, especially in software, 1,000 times slower. And it's 100 times slower if it is hardwired. So you don't want to you try not to use it. What we usually use it for, like the Diffie-Hellman, we use it to connect two people on the internet, and we'll use Diffie-Hellman keys to transfer symmetric key, pre-shared key. So we'll use Diffie-Hellman to transfer the symmetric key, the pre-shared key to the receiver, and when he's transferred it, he's done. He doesn't do anything. Then we'll always use the symmetric key to encrypt and decrypt the data. And when the lifetime of the symmetric key for that VPN is gone, Diffie-Hellman comes back in and he sends us another key using the private and the public key idea. Is that clear? So we always use asymmetric encryption algorithm to transfer symmetric keys, especially for VPNs. That's what it's most widely used. We may use the RSA, for example, when you're doing SSH, because you're sending a very small amount of data when you're connecting to a router and a switch and trying to configure it. But when you're talking about VPN and trying to send a lot of data, it becomes really, really significant in terms of traffic-wise. All right, so you have those three different types of asymmetric algorithms, and I explained to you how this works, right? So Bob will use, private key to encrypt the data, and so on. So you take the data, you encrypt it, you send it out to Alice. Alice will receive the data and then decrypt it with her private key. That's how it really works when you are actually doing things on the internet. Okay, so we just explained all of that. Okay, now let's talk about integrity. We can achieve also integrity when we are encrypting the data. So, but when you're sending the data, we're going to make sure that I talked about non-repudiation, authentication, right? So we explained all of that. Here's how Diffie-Hellman works, the asymmetric. Please write down all these bullet points for Diffie-Hellman. What Diffie-Hellman does is use mathematical equations, okay? And they really don't share any data. They just need to agree on when they calculate a number, and that number that comes up at the end is the actual key that they're working for. So let's say we agree on, we're going to work with, this is just an analogy, paint, the yellow paint. I'm going to use a secret color to mix the paint with, which is a secret number to raise the power. It's really, they use module and modules. In class, I can explain it to you. I have a sheet on how they actually work mathematically. And Bob will use the blue color. So these are secret. They don't share this information with anyone. So when you mix these numbers, you'll get these colors. You send me yours, the mixed paint. I send you my mixed paint. When you use your secret paint that you use to mix with the yellow, you are going to get a special number. And when you use the blue, your secret color, to mix also the yellow, to mix with what you send me, I'll come up with the same one that you came up with. So this is the keys. These are the pre-shared keys that the sender and the receiver will use. So let's say Alice is the sender, Bob is the receiver. Allison and Bob will agree on one number, and they will use a raised number that they don't share with each other. They'll do some mathematical equation to come up with some number when they mix these, right? And then they give us whatever is encrypted. So if anybody captured this encrypted data, they don't know what the hell is going on. And then we'll use our shared key to come up with a new key. It's really amazing how this works. And with these numbers are very, very large, you can come up like the secret color. It's almost impossible to figure out what's going on. And these will be the pre-shared key. That's what I mean by you don't really actually take a key and send it. You just come up with a key that we both agree on at the end. That's what DH does. And if the number of bits that calculating it is larger, it becomes almost impossible to crack. So the higher the DH group, the better, the more secure it is when you are creating symmetric keys over the internet. But it takes longer to calculate, right? The higher the number takes longer, but once you're done, you got the keys, it's all over. Then you start sending data. But by the way, you don't want to, if you're going over the internet, and you don't want to use the same key all the time, because given enough time, somebody might figure out what it is. So when you're doing VPNs, every once in a while, you got to use DH to create a new symmetric keys. Okay, just remember that. So please write down the following DH groups that are supported by Cisco operating systems from 1 to 16 and how many bits they are. Okay. So now we move on to the public key encryption. So let's talk about digital signatures. What is a signature? Is usually signature is to it's unique to the person who is sending the data. So if you sign a check, you know that your signature is no one can replicate. Correct? Digital signature is supposedly to provide the same thing. We want to provide authenticity, integrity, and non-repudiation, like I discussed earlier. Now, we do digital signatures. Write these two notes down. Digital signatures are commonly used in two situations. Code signing. This is when you are purchasing a software and you want to download it. What they do is they digital sign the executable file that's going to install the software, and you double check it, and you're going to make sure that that software came from a legitimate vendor and it is secured, and so you'll be able to download it and install the software. That's what code signing is for. Digital certificates is I'll have like a license that I can use with my public keys that I can use to download and upload stuff with another server. And I'll discuss this digital certificates more often. So when you are, let's say you're going to your bank, you'll be able to use your digital certificate to connect to it. Anytime you use an HTTPS, you're using really the digital certificate. And what's on the digital certificate? Your public keys. I'll discuss more of that in a few minutes. So again, for code signing, it's really for the software. So please write these 3 bullet points down. Digital sign coding provides several assurances about the code. The code is authentic, came from the source of the publisher. It hasn't been modified since left the software publisher, and so on. Okay, and so the publisher undeniably published the code, right? He cannot repudiate that. All right, so digital signatures. So here's an example of how digital signatures work. So let's say you have, I don't know, Chase Bank, and you want to do some online banking with them. So what they do is they go to an authority called certificate authority. I know we're going to be discussing this later on. I'm just giving you a scenario of how this may work. So Chase Bank will go to a certificate authority and it will say, hey, we want you to create some digital certificate for us. So they'll verify Chase Bank. And what they do is they're going to generate the private key and the public key for them, right? And they'll give Chase Bank the key, their certificate, with their private key so they can put on their servers. And when I go in and let's say I want to do banking, they'll give me a digital certificate that has the public key in it. So now I can verify that this certificate came from reputable certificate authority, a certificate authority that I know that is has good reputation, right? And so I verify, and I will be able to communicate with the Chase Bank servers using my digital certificate with their servers, and they'll have their private servers. And when I send data to their servers and their server sends data to my computers, they can verify that these digital certificates are authentic because they came from an authenticated certificate authority. This is like I go and get an ID or my what do you call it? My license from the motor vehicle, right? The motor vehicle is the certificate authority. The police knows, everybody knows that the motor vehicle is an authentic authority that gives out these certificates, right? So once I get my license to get all the information I have, I can go and use my license to buy alcohol, for example. If you wanted to buy alcohol, I can drive a car using my certificate. So if somebody looks at your certificate and says, okay, oh, you're allowed to drive so and so, you're allowed to go into this place because you have that certificate is being used, right? So he's a typical, so you can actually go into your computer and find out all the certificates that you have. But here's a typical certificate that came from Cisco when you're connecting to Cisco. And there are tabs in it, and here they explain what these digital certificates. So the main digital certificate that you have on your computer is they have your public key, right? And you'll use that key to encrypt the data and send it to the server that has the private key, right? They also have those digital certificates from the same place. All right, so that explained what a digital certificate is. Let's look at the authorities, the public key management. This is the motor vehicle. So you go get your certificate from there. They give you a certificate, the public key, or a lot of information that's on there, and they'll give it to you. And then you can use this with the public key and access your bank, right? Because they are the one who hired this is the bank, let's say, right? The bank will also get the private key from the certificate authority. They give them a certificate here. So now I can use my license, my certificate to communicate with Chase Bank, and Chase Bank can talk to me without any problems, right? We can talk to each other. This is pretty much how the whole internet HTTPS pretty much works, right? So please write down for the public key management, write down all of these bullet points, because I'm afraid you will get tested on it down the road, right? So there is the public authority. So there's a public certificate, PKI certificate authority. Think of it as like the motor vehicle, and they have a database of all the certificates that's being saved. Now, it's not one central place. Anybody can can be an authority, but you have to be well known. Microsoft, they're certified. There's Digi certified. I think there's Baltimore, one of them. VeriSign is another certificate authority that is well known. By the way, so for the infrastructure, please write these 4 bullet points down, right? Because that's good to know. Moving on. All right, so I get a certificate, you get a certificate, and now we can talk to each other with our certificates, and we don't have to deal with anybody. We can authenticate each other, right? Now, also, the certificate authority keeps track of the registration authority. There's subordinates that you may have. You don't have to go to the motor vehicle. They may have a little branch office next in your city, right? So they can offer digital certificates too, right? And the digital certificates that you get will have a class number on it. The higher the number, write this down. Think here, write this down. So the higher the number, the more rigorous was done to investigate before you get, the more authentic those digital certificate is going to be, right? So the higher the number, the more trusted the certificate is. That's what I wanted to say. So please write that down and take a picture of these 5 different classes of your certificates. And again, like I said, you can use, there's the root certificate authority, and there may be some subordinates. So you may get your certificate from here, but they keep track of everything, right? So this is a hierarchical method for the big certificate authorities to make sure that they can keep track of it, right? Okay, so to make sure that everybody, when they are creating digital certificates, not everybody come up with their own standard and how the certificate is going to be. So the IETF, So the Internet Engineering Task Force came up with a standard called the X.509 Public Key Infrastructure Certificate Policy. So please write that down, ITF X.509, and that is used. Everybody needs to create certificate according to this standard. Okay, so please write these down right here. These 4 bullet points. SSL is a secured web or X.5 version 3 websites. They use that, the SSL and TLS protocols for web browsers. So that's what you use. Number 1, for the certificates, they use the standard 509 version v3 and so on. Okay. So the X.509 key infrastructure certificate policy is to make sure everybody follows the rules, the protocols on how to create certificates. All right, so the certificate authority has to keep track of all the certificates that are created, authenticate them, revoke them if they have to, keep track of what's being revoked, and so on. All right, so finally, let's take a look at the applications and the impacts of the cryptography that may have. The following will provide a short list of the common uses of PKIs, everything pretty much. Please write all of this down. I want you to at least read them once, twice, maybe 3 times, so you get familiar of why we need cryptography. You're using it for any certificate-based authentication when you're trying to connect, when 2 people want to communicate with each other over the internet in a secured manner. They may use the SSL. HTTPS, anytime you type in HTTPS, for example, website, you're using encryption, you're using PKI applications. Secured network traffic, when you're creating VPNs, you name it, almost everything. Securing an email and its attachment, instant messaging, encrypting your hard drive whenever you need it using EFS, code signing like we discussed earlier, securing your flash drives, encrypting it. See, everything almost. Without the PKI applications, it's without cryptography, the internet would have never really expanded so fast. All right. So these are the typical signatures that you may have. So the encrypted network transactions, threat actors may use the SSL to introduce regulatory compliance, viruses, malwares, and so on. So you have to double check. They will double check your certificate. So if somebody sends you anything, even when you connect to a wireless network, they may ask for the certificate. And if they cannot verify the certificate that you have, they'll say, hey, wait a second, something is wrong. You'll get a certificate validation error. You may, they'll ask you, do you want to still communicate with that device or not? And you may not have to if you don't want to. Okay? So, but here's another problem. So network monitoring becomes very hard. So if you want to watch the data that is flowing in your network, if somebody can encrypt the data that is traversing the network, it becomes an issue for you. So if somebody is stealing the data, wants to go into your network, you won't be able to see the intruder that's coming in, the threat actor, because his data is encrypted going through your network. And you won't be able to see what he's trying to steal or take. So how do you protect against this? Please write down these 4 bullet points, right? And the most important one I want you to take a look at is the Cisco SSL appliance to decrypt SSL traffic. So they'll be able to decrypt the data that's being sent on your network or coming into your network, and then they send it to an IPS system to make sure it is okay. All right. So a security analyst must maintain a good understanding of the different types of cryptographic algorithm and operations to be able to investigate cryptography security incidents. So you need to know The two main ways cryptography impacts security investigation. If you are investigating something, an incident, and it has something to do with encrypted data,